Hello guys, so in today's video we're going to learn about device trees and platform devices, okay? The idea is that now we're going to make our Z board recognize that there is some device, okay? That there is some IP core working in the FPGA, okay? And through device trees we're going to communicate to the kernel that there is a hardware there and that there is a driver that will be responsible to control the device. Okay? Hope you guys enjoyed. I'm going to switch to the board and probably then some slides as well to explain a little bit more about these concepts. Okay? Hope you guys enjoyed. If you guys like, give me a thumbs up and let's start. Okay guys, so what we're going to learn today, okay? In the previous video, okay, we created an IP core. Okay, by the way, this IP core has been mapped at this address, okay, and what we're going to learn today is how to use Petalinux to create a device driver skeleton, okay, that is going to detect, okay, and remap this IP core to the virtual memory, okay. Basically, what we need in order to do that, okay? Imagine that here is our project in Vivado, okay? And we know that the Vivado, they create the bit stream, and when we export the Vivado project to Xilinx SDK, for instance, we have a hardware description, okay? The idea is that Petalinux, besides creating the device driver skeleton of all these of this IP core here, he actually going to use this hardware description, okay, to create what we call a device tree, which is just a file, okay, consider this as a file that is going to describe to the kernel what we have available in terms of platform devices, okay. Then with the bit stream created, the device tree, the Linux image and the rootfs, we're going to create our image to place in the SD card, okay? So let's see today how to do this. I'm going to jump to some slides to explain better what we're going to do and what we need to learn, and then we go to the lab and see how it goes, okay guys?
Guys, so continue our class about device drivers, okay? Now let's go to the topic of device trees, okay? I'll read the text, then I explain a little bit better to try to give you the best knowledge that I can about this. So, device trees, okay? They are structured text files, okay, that are compiled with a tool called DTC that is inside your Linux source code, and given to the kernel on boot time, okay? When you boots the kernel, it boots the kernel image plus a device tree binary image, let's say like this, okay? So they serve to provide some information about the hardware that the kernel will handle, okay? This is an attempt to tackle the growing number of ARM boards that have different hardware, okay? The idea is that the same kernel will run on different boards with different device trees, okay? The kernel will parse this device tree and instantiate all drivers needed, okay? Here we have an example of a device tree entry, okay? What you need to pay attention is this compatible field, okay? Basically, the compatible field is used to indicate the kernel which driver will handle this hardware, okay, this device, okay? The interrupt is the interrupt property, okay, contains the number of the ERQ, okay, of the interrupt, and the reg means what is the physical address and range of that hardware, okay. So to explain again, device tree is just imagined as a XML file, okay, that is going to be given to the kernel at boot time, and you give to the kernel the information on what hardware you have on your board, okay, and which device driver will handle that specific hardware, okay. So platform devices, okay, and these are really connected to device tree. device trees. So on embedded system, devices are often not connected through a bus, allowing enumeration, hot plugging, and something that provide unique identifiers for a device. Okay, they are normally connected to the CPU through some kind of AX interface or any memory mapped interface or some kind of I2 bus. Okay, maybe it's better to explain this with an example. Okay, if you plug your USB disk in your Linux machine, the Linux will automatically detect this USB drive and enumerate and give him some kind of identifier. Okay, the case of the platform devices, you don't have this. Okay, you have some device that is placed somewhere in the memory mapped part of the CPU, and you need somehow to create a device driver that control this guy. Okay, so that is the basically, if I could explain, simplify what platform devices are simply devices that are not automatically detected by your system. Okay, you need the device tree to indicate to the kernel, like, look, kernel, I have some hardware A that is in a certain address or something like this. Okay. Here there are some complete examples, okay, of platform devices, and you can click on them to have a look, consider source code. Okay, when you are creating device drivers for platform devices, you need to have this structure here. Okay, is the platform driver. Okay, and the most important thing that you need to do with it is that you need to pass a function pointer to the probe, remove, okay, and the structure driver as well. So basically this is the remember when we look on the FOP structure that we need somehow to give to the kernel some function pointers, some callbacks that will be called when the probe remove occurs. Okay, so for instance, when the probe will occur, okay, imagine that you load a module, okay, and the module is somehow compatible, okay, with some hardware that has been given to the kernel through the device tree. Okay, at least some some device information. So when you load the module, the kernel will detect that it has some device that is compatible to that device driver, and at this moment the probe method will be called. Okay. And when this probe method occurs, okay, there you need to do some stuff like IO remap or read some information that also has been passed to the device tree, but we're going to touch this subject in the future. Okay. So just to illustrate a little bit better, imagine that here we have a hardware called of type UART, okay, and he's basically compatible with the IMX28 AUART driver and the IMX23 AUART. Okay. Some important stuff. It has this physical address here, okay, with this range. Okay, so it would be this address here is really the bare bone physical address. Okay, it has this interrupt number, okay, and some other information. So when you create the device driver to control this hardware here, okay, basically you need to have this platform drive structure, okay, that points to the callbacks of probe and stuff like this, and you need to have this structure here of device ID that basically you say to which hardware this device driver will control. Okay, and basically this guy here, this compatible field, need to match to the compatible field that you have on your device tree. Okay, and after this is detected, the probe callback is called. Okay, you can use some default functions to get for instance the reg field. For instance, if you just type platform get resource and you ask IO resource mem, is basically going to return this a pointer to the description of this physical address. Okay, If you call as well platform get URQ, okay, it's going to get the interrupt number and stuff like this. Okay. How you create a device driver in Petalinux? Okay. As you may suspect, Petalinux also have a command to create a skeleton device driver. Okay. So you just run Petalinux minus create minus t module minus n, the name of a module, minus minus enable. Okay, and this will just create a skeleton of a device driver. Okay, and just to start, the only thing that you need to do is to change the compatible field, okay, with something that is located in your in your device tree. Okay. Then you just do nothing else. You just run these commands here: Petalinux build -c rootfs and the name of the module that you create. If you want to check some errors, you just go to build log of your project. Okay, and here is just the place where the module will be created. So just to analyze a little bit the code that he generated, by the way, it's quite simple. Here are just the headers that you need to include. Here is just a structure that will hold the physical memory address and range of our device. We are not going to use the interrupt now, but this is just an interrupt handler. Okay, this is the method remove, sorry, the callback that is going to be called when you remove or you do rmmod, when you uninstall the module of this device driver. This guy will be called. Okay, this guy here of device ID is really where we should change to actually the compatible field to match the device on your device tree. Here, this structure here is where we will point the callbacks of the probe and remove. Okay. What else? When we init, actually the init of the module, we call platform device driver register to register device driver, a platform device driver, and actually initialize all the platform interface for you. Sorry, the platform framework. And most important is the probe method, as you may imagine. Okay, so what the probe method does? First of all, he gets the reg field of your device. Okay, let's just go back here to a device 2, device 3. Okay, so basically we are interested in this guy here. Okay, and its range as well. So that's what is the probe method is doing. After he got this, he just allocate a memory with kmalloc, I don't know how to say that. To hold the information of your physical address, but the most important is those two calls here. First, the request mem region. Okay, basically you are asking some, you're telling the kernel that physical address and range will be binded to this hardware alone. Okay, and the IO remap, which basically will give you a virtual address that represents that physical address that you have here in your device tree. Okay, so as I mentioned before, when you are in the module, we are still using virtual addressing. Okay, so even knowing your physical address here at this point here of your IP core, you cannot access that directly. Okay, you're going to the kernel will not allow this. So you access physical memory through the IO remap through a virtual address. Okay. After this is done, this is actually a continuation of the probe method. He's just going to print some information. Okay, and basically this guy here is the most important for you. It's like it's going just to say the simp module that has the physical address A is mapped to the physical address B, and all of your work to control your device should be done reference to this virtual address. Okay, Let me just jump because this is just defining the IP core that we created. Okay, this simple ALU. Okay, here is again his physical address. And here will be the result after everything is done. Okay, so basically here, as I shown, he would say when we load this this module, okay, he will say that this physical address here has been mapped to this virtual address. Okay, and all the registers that we should control for, if you guys remember, is the register A, B, C, and op, should be offset from this base address here, for this new virtual base address. Okay, here is just to show how the bare metal version was done. Okay, so if you guys remember, we just have some offsets related to our base address, but now will be actually need to be related to this address here. So it will be like 609 6000010, okay, or something like this. What else is cool? I'm going to show that now. Actually, this is the first thing that we should do before we create the device driver. I just wrongly put this part out of order. Okay, so basically, after you went to Vivado and you generate the bit stream and you did all that, you need to somehow inform Petalinux, okay, about the hardware that you're using. And basically, this guy will be the one who is going to create the device tree for you. So basically, you just call Petalinux config, get hardware description, and you point to the place where your hardware description has been exported. Okay, this is that phase when you go to Vivado and you export the hardware description to the Xilinx SDK. Okay, don't worry, we're going to do this on the lab, so no problem at all. After the device tree is created and you do the Petalinux build, you need to generate the boot.bin again, okay, to include your new bit stream. Okay, otherwise you're going to have the device tree, but the hardware will not be there physically on the FPGA. Okay, and let's stop for today. I just showed the lab. Okay, then after this video we're going to actually basically recreate all these functions here, but using the virtual address. But let's do some small steps at a time. So let's just point Petalinux to create the device tree for us based on the hardware that you create in Vivado, and create this device, platform device driver skeleton with Petalinux, and then we put on the Z board and we turn on and see what happens. Okay, guys, so let's go to the lab. Okay, guys, so as we explained in the board, the idea of this video, okay, is basically to instruct Petalinux to recognize our hardware, okay, which is basically our Zinc processor and our simple IP core that is just ELU, okay, that is going to do some arithmetic operations. And the most important thing here is that after you generate the bit stream, okay, we need to export the hardware information, okay. So we just go to File, Export, and well, that's it. Okay, so this will create a list, okay, a kind of description with your memory address and the IP cores that are there, okay. And Petalinux will use this with the to create a proper device tree that represents our hardware design, okay. Okay, guys, so now that we export, okay, our hardware information, okay, we're going to use the command petalinux config, okay, --, get hardware description, okay, and we pass the directory where the Vivado exported, okay, the hardware information, and it's normally in it's like name of the project .sdk design wrapper hardware platform. Okay, so let's press enter. By the way, Vivado must be installed in your computer, okay. This is my Linux machine, so it's ready already with Vivado, with Petalinux installed. And After this is done, he's going to generate a device tree, okay, on this directory here. So I'm just going to already copy this guy, and we can take a look later. So cool. So let's go to this directory, and we can see, for instance, in the pl.dsi, okay, we can see that an entry has been added, okay, and is related to our IP core, okay. So basically, here is just saying that our IP core base address will be here, okay, and is going to have this range, okay. It also say the compatible line, so we need to, when we create our IP core, when we create our device driver, we need to use this, okay. And well, now that's it. There is also the interrupts that you're going to see in another video, but now up to this point, this is enough, guys. Okay, guys, so now that that we import into Petalinux the information of our hardware, okay, we need to call this command here, Petalinux package, okay, --boot --fsbl, and we need to pass basically the first stage bootloader, okay. This is normal, this is going to be always the same, but what is important here is this guy here. We basically now asking that Petalinux create a new, let's say, the SD card image, okay, but adding as well the bit stream, okay, of the IP core that we have. No, it's better to explain that this bit stream here will have everything that your Petalinux project, okay, need, okay, and is pointed in Vivado. So basically, we're just updating. We asking here to have the latest version of the FPGA, okay, and include this on our boot image. So we just type enter, and cool that this error appear. The guy is just complaining, saying that he cannot find this command here, but it's really easy to solve this. So basically, guys, what we need to do is call source, okay, and point to this script here that is going to configure all the paths, all that's needed, okay, on Vivado in order to create a bit stream, okay. So now we run again our Petalinux package. Again, the idea is that we are going to include our bit stream on our boot, okay, and so then it's working, okay. I already created this this module, so I'll just say another name like sync mod 2. So Petalinux create -t modules, okay, -n name of the module, -- enable to automatically add this to your rootfs, okay. So let's do it. And well, the first thing that we need to do after this guy is created, okay, is that we need to change the compatible string in our device driver, and basically that's it. So if we go to the directory components modules, okay, we can see that we have now two modules, okay. This one is our next video because it's already created. There is some logic inside this guy already. And if we go to this directory here and we just change what we go to change, here, guys, so basically this part here is the compatible part. Here we need to match on what we have in our device tree. So let me just go to the previous model that I know that is already working. Let me just go really to the end. And let's just copy this. Okay. By the way, guys, I'm using VI here, but you can use the editor that you want, okay? Just because, I don't know, sometimes I'm more used to this guy. Okay, so let's close it. Okay, here, cool, here. So we just go in your project directory and go to subsystem, Linux, configs, and device tree. And we just open the file pl.ttsi. So here, you see? They match. It's the only change that you need to do. Okay? So let's go back to our project directory. And now we need to run Petalinux build. Okay? Now we're going to compile our module. Okay? We're going to check because we use enable. So in theory, when you create the module with enable, he should automatically add to the rootfs. But we can just check it after this is done. So compiling again our Linux, and let's see how it goes. Okay, so here we can see that he actually add our modules. Okay, but if you want to check it again, you just can go petalinux config -c rootfs. Okay, and he's going to open the menu config, and we can see that you have here both modules. Okay, so guys, basically now what else we need to do is go again and copy all the directory that we have in the /tftp boot. Okay, the boot.bin, I don't know, copy all the guys to the SD card, put on the Z board, and then turn it on, and let's see what happens. Okay. Okay, guys. So now let's go to the last part of our lab. Okay. We already have booted our Z board. Okay, and we have already set up the Ethernet connection. So if we just come here and do an SSH, oh sorry, 192.168.0.10 for instance. Okay, password is root. Okay, and if we go to the directory lib modules extra, basically this guy here, we have this actually this is our end model, but this guy here is the model that we just created now for Petalinux. Okay, so let's just run the message to see if there is any other message, and it's not the case. Okay, by the way, oh sorry, this is our Z board. Okay, and let's just install this model here. Okay, and look what happens. So if you now run the message again, we can see that our model, okay, this is, by the way guys, this is called in the probe callback of our device driver. Okay, so basically we can see that this this device here, okay, on the physical address 43C000, okay, has been mapped to a virtual address 609.60000. Okay, so basically what happens in the Linux. Okay, so the device tree, okay, detected that there was the Linux detected that there was indeed a device, okay, that the device tree expose, okay, and when we load the module, okay, the kernel detected, okay, so there is indeed a device compatible, okay, with the compatible string of this module that I'm loading now. So then the probe, so he calls the probe method, okay, and then the probe method will remap a virtual address from this physical address here, okay. So for today, that's it, guys, okay. The next video, we're going to actually add now the logic on the on this module, okay, which is basically the source code of the previous module. And hope you guys enjoyed, and see you guys in the next video, okay. Any other question, just send me a message, and if you guys having problem with this as well, just send me a message saying what is happening, and I'll try to help, okay. See you guys in the next video. Bye bye.